I'm going to restart the recording for this one. And anyone who'd like to stick around for the week one
Thank you.
conjecture, free to do. Thank you. All right. So for those of you that are staying for the week one part, is there any particular conjecture that you guys feel like it's harder than another for you to prove? We can start with the hardest one. There were 6 of them. Or we can start with like one of the easier ones and talk about how to do the proofs and then move on to a harder one.
What about the product of an even number and an odd number is even?
Okay, perfect. Yep, let's do that. Okay. Thankfully, this one will be easy to type. There's no exponents. Okay, so we kind of went through the theory in last week's office hour, so I don't want to talk so much about that. I want to talk specifically about how you write it, because I think that's sometimes just as hard as the theory behind it. So the first thing you want to do when you're writing up your proof is you want to clearly state what your conjecture is. So how would you guys state what our conjecture is? And Natalie, I think you said it. So if you want to, you can just state it again.
Yeah, so the product of an even number and an odd number is even.
Okay, perfect. So this is what we want to prove. And in any type of proof, you always want to go back to the definitions, which is why step 1 in the project guide was specifically defining what even and odd numbers are. So what is the definition of an even number?
It's the 2n.
Perfect. And n can be anything. So, or any integer. So you don't have to use n. You could use x or m or a or b. Like it doesn't matter what variable it is. The important thing is that you are doing 2 times an integer. Because any even number can always be expressed as 2 times an integer. So the way that I would say this, because what I want to prove is that the product of an even number and an odd number is even. So I'm going to say let's see, how would I say this? The expression 2n represents an even number or any even number when n is an integer. And does that make sense to everybody why that's the case? That any possible even number could be represented in that way?
Yeah.
Okay, so I've got an algebraic expression for first part of my conjecture. I have an even number. Now I also want to have an odd number and I'm going to multiply them together. So what type of expression would we use to represent the odd number?
So you would say the expression 2m plus 1 is
Did you
representing
say n or m?
m.
M. Okay, perfect.
Is representing any odd number or any odd integer.
Specifically when m is an integer. Because like if m was a decimal or something like that, it wouldn't necessarily be an odd number. So it is important that you specify that it's when it's an integer. And it would actually probably be good actually for me to specify that this is by the definition.
Okay.
So I'm explaining where this fact came from. So by the definition of even numbers, the expression 2n represents any even number. Same thing here, by the definition of odd numbers, the expression 2m plus 1 represents any odd number. Now, this is good that we're using two different variables here, because if you used n twice, it would not be proving that any even and odd number, when you multiply them as even, it'd be proving that an even number and its odd number that's right after it, that those are always even. Does that make sense why you have to have like different variables there? Because if they were both the same variable, so maybe I'll like type this out. So this would not be the correct way to do it. If you had 2n and 2n plus 1, if you chose any random integer, like say n equals 5, like that would be the even number 10, because 2 times 5 is 10, and the odd number would be 11. But it would always be like the next odd number because the integer was the same. But when you make the integers two separate variables, then it allows the even and odd numbers to be far away from each other, or they could be right next to each other, but it could be either. So letting them be different variables is really important. Is everybody good with that part? Okay, so I've got my two expressions for these two parts. So I've got my even number, I've got my odd number. And ultimately, what I want to prove is when you multiply these together, that the result is even. So what we want to do is we want to multiply 2n, and I'll type up my reasoning in just a minute, but I want to multiply these together and ultimately have this equal 2 times some type of integer. That's like the goal of the equivalence I'm trying to prove, because I want to show when I take my even number and I multiply it by my odd number, that it equals an even number, which is defined to be 2 times some integer. And we'll define what that integer will be as we expand this. So this is kind of my goal of what I want to work towards. So if I want to type this up, I would say to show that an even times an odd is even, I will multiply the expressions 2n and 2m plus 1. So I'll do my calculation here and I'll say, okay, 2n times 2m plus 1. Now, this, the way that it's written right now, is not in the form of 2 times an integer, because like I need to have a 2 times integer stuff. So how could I simplify this to get closer to having it be of the form of 2 times something?
Don't you need to do a single FOIL where you're doing 2n times 2m and then 2n times 1? And that
Yep.
will allow you to pull 2 out of it, to factor 2 out of it and get to the format you're looking for.
Yep, exactly. And that single FOIL idea, that's called distributing. And the way we can justify it is with the distributive property. Because the distributive property says if you have something multiplied by a set of parentheses where you have like things added together, that you can multiply each individual thing and then add them all together. So in this case, I would say by the distributive property, this expression is equivalent to, and then I'd say 2n times 2m plus 1. So that's my original expression equals, when I distribute the 2n to the 2m, I get 4nm, and then 2n times 1 gives me 2n. So this is simplified in the sense that there's no parentheses now, but it's still not in the form I want it to be in, because I ultimately want it to be in the even number form, which is 2 times an integer. So is there any way that I could get a 2 outside of the parentheses? Or like have like 2 times stuff?
Could you pull a 2 from the 4?
Mhm.
And from 2n, pull them for both.
Yep, exactly. So that's called factoring. So by factoring the 2 from both terms, I get, and I'm going to stick with this original expression. Since those are like the even and the odd numbers multiplied. And I'm going to say that this is equal to 2 times. If I factor out the 2 from 4 times n times m, what's left?
It's 2nm
Mhm.
plus n.
Perfect. Yep. So factoring is basically like reverse distributing. So like in this case, we distributed the 2n to the 2m plus 1. So it's still by the distributive property. So if you wanted to, you could add that in to justify the property that makes it so you can factor the 2. But essentially we're like undistributing a 2 from those 2 terms, which gives us this. Is everybody good with this so far? And this is the form that we're trying to get. We have 2. And so now, like we have 2 times something. So now the only thing we need to do is justify that this really is an integer. So if you have 2 times an integer times another integer plus an integer, what is it that guarantees that that whole thing is going to be an integer? Like what property could we use to justify that?
Is it just the definition of integers?
It's properties of integers, yeah. So like one of the things about integers is if you take 2 whole numbers or 2 integers and add them together, it always equals an integer. Same thing if you multiply it. So we could justify this by saying, because the sum or product of integers is always an integer. And if you wanted to get like super specific, you could say, oh, what's the name of that property? I think it's the closure property because integers are closed under addition and integers are closed under multiplication. That's the technical form for it. I'm okay if you just say that the sum and product of integers are integers because that's something we use a lot. And so you don't have to get super technical, but if you wanted to, that is the property. It's the closure property of integers over addition and multiplication. But basically, because the sum or product of integers is always an integer, the expression 2nm plus n is an integer, and if you want, to, you can call this a new variable. So you can say which I will define as being the integer, I don't know, k or something like that. Therefore, this expression equals 2 times an integer. So by the definition of even numbers, and basically I would just restate what I just proved here because the fact that I, through this algebraic manipulation, showed that multiplying an even number times an odd number equals 2 times an integer, which is an even number, that proves that any even times any odd will always equal an even. So I can restate that and say the product of any even number and any odd number will always be even. So this is kind of the conclusion to my conjecture. Does that help with like how to write out the proofs? And I can kind of like go back and highlight the steps of it, if that'd be helpful. So like the first thing we did was we said what the conjecture was we're trying to prove. So this is like the goal of what we want to prove. Then we took each part of the conjecture and wrote an expression for it using the definitions of even numbers. So since we want to show that it's an even number and an odd number, I defined these two expressions and justified the definition of them because of the definition of even and odd numbers. And then I multiplied those together because I want to have the product of an even and an odd number. And then I used various properties like the distributive property or factoring. On some of the problems, it will be like the associative property of multiplication or the commutative property where you can rearrange the order of the terms. But basically, you use whatever properties you need to get the expression in the form of whatever you're wanting to prove it is. So in this case, since we wanted to prove it's even, we manipulated it until we had 2 times an integer. And then we explained why this has to be an integer because of the properties of integers. And then we concluded that it would always be an even. And if you want to, you can redefine this parentheses stuff as a new variable, or you can just skip that part and you can say, because this is always an integer, therefore the product is always even. So like you could kind of cut out all of this part and just like make that one sentence if you wanted to. Any questions on that?
So
Awesome.
resubmit week 1, right?
Say that again.
We can resubmit week 1.
Yep, totally. Yep, and you can resubmit it as many times as you need to. So if you resubmit it and I'm like, oh yeah, like most of it's right, but you need to tweak these little things to get full points, you can resubmit it again.
Okay.
And that's true for any of the assignments in this course. Well, except for the final, but all the other assignments.
Thank you.
Yeah, of course. Do you guys have any other questions that would be helpful to go over? Jody, for the most part, yes. Sometimes I'll put in like a little comment that says like, you do it this way. So most of the time though, it like needs to be fixed. But sometimes it's just like this is another option of how you could have done it. But when I do it that way, I'll usually like say, this is correct. And another way you could do it is also this way. But for the most part, the annotations are things that need to be fixed. Yeah. Right. If it would be helpful, I'm fine going through one more proof write-up if you guys want to, or we can end it here. If you do want me to go through one more proof write-up, let me know which conjecture you'd like me to talk through. Yeah, of course. Okay. I'm not seeing any comments or requests. So I guess we can end it there. If any of you guys have anything you want to talk with me one-on-one about, I'm happy to stay after however long we need to. But I will end the recording here, so that the recording that's published doesn't include any of those conversations.